Hi everyone. So we are going to start this first seminar at the interface of machine learning and meaningful games. So we decided to start this seminar in order to have more and more discussion. We hope it can spark like more interactions and collaborations between the two communities. So today we are very happy to have Xin Guo, who accepted to present her recent work on a meaningful perspective for multi-agent reinforcement learning. So, yeah, Xin Guo, the floor is yours if you want to start.
Yeah, okay. So thank you for the nice invitation, and it's really a great pleasure to talk to the group who actually I was just talking to Sarah and Matthew. Half of the people in mean field games and reinforced learning here is actually in this group. So I'm really looking forward to these opportunities to discussions with various things. So please feel free to stop me at any time. This is the work is based on a sequence of works starting from 2019 and all the way to the current paper we're revising. So it's really also so from 2018 and now in the era of mathematics that's pretty short, but in the era of machine learning it's almost feel like history. So this is based on a joint work with Hao Tian, who is actually a PhD student at Berkeley, and Xiaoli Wei. Many of you already know. She used to be at working with Hui Yin, and then coming from France, and then being a postdoc with me, and now she went back to China in Tsinghua Berkeley Institute at Shenzhen. And Ren Yuan was my student, and then went to Oxford, and now coming back as a professor at USC. So this is actually what I'm planning to do is really starting with just to in case there are other people who are not familiar with these topics, just talk about a brief history of how the multi-agent reinforced learning and mean field is really coming into together. And the focus of this one, although it's mean field, could point to mean field games or mean field control. And what I'm going to really talk about is mostly on mean field controls, and then some of the latest work, especially the last piece of learning mean field controls when there's a network structure. That's our most latest work. And before doing that, I think I will talk about in a more general case without the network structure how the mathematical foundations of mean field control with learning is set with starting from dynamic programming principle to the design of learning algorithm. And to start, what I think the reason that this lecture series is really fascinating in the sense that if you look at the entire machine learning community, one of the fascinating area is really reinforced learning, and it's really one of the most active area. One of the reasons I think behind it is there's a very solid foundation, mathematical foundation behind it, which is really the Markov decision processes, and it's built on this solid foundation and vast theories and a reservoir of theories. And on top of that, you grow the trees of learning, where you take a Markov decision problems where you have the reward function, discount, let's take infinite time horizon problem. Then you have the dynamics of the Markov problem, you have the reward, and you have the objective functions. And then it has been developed over many decades. And then the reinforced learning built on top of it is to say, what if we have a Markov decision problem that we have unknown dynamics and unknown reward function, and that really set the roots of reinforced learning in a very solid and very fertile ground. And then if you actually come from the control perspective, then the classical Markov decision problem, usually we spend a lot more time on deterministic strategy, or what we call strict control, that's what control people are more familiar with. And of course, there's also, when you get to the learning, then you start having these strategies based on the distributions or mixed of these actions, and or in economics called randomized strategy, is over the probability measures over the action space. And this is really fascinating, and you can find a lot of mathematics behind it that, in relaxed control that were developed in the 70s and 80s, but then there was really not much follow-up on it. But now you look at machine learning, then there's this reinforced learning is really exactly where this randomized strategy, or in economics mixed strategy, is about. And that's really the essence of what reinforced learning is exploration, exploitation. You need this concept of relaxed control. So therefore, I think this is really fascinating that the whole reinforced learning thing has become such an active area. And so you have this background, and then the mathematics that has been built in the Markov decision problems, where you have the Bellman equations for the value function, you have the policies, iterations, and all the things. You can pretty much translate it into the learning literature, where instead of just focusing on value function, you can also think about the Q function. So learning emphasizes more about the process than the end result of the value, and therefore this Q function creation is very natural. It's not just paying attention to where you are, but also paying attention to what kind of action you take to actually get to the learning and get to the optimal value. So in this case, the Q function really is very tight to the value function, but really reflecting with the value, the learning components, and correspondingly all the dynamics or the Bellman equations for the value function in the Markov decision problems, and all the policy iteration, value iteration, is really very natural with all this recursive equation spelled out from the Bellman equation. So this is, of course, this is just everyone knows it very well, and this is what we teach for reinforced learning 101. When you go to the multi-agent reinforced learning, of course, now you're thinking about a lot of agents rather than one, and then you have this complicated interactions starting from all this application now, Zoom or Google Meet and Uber, and online ad auctions that Google is really pioneer on that, and then to the finance, to optimal execution and crowded short, and so on and so forth. And in all this multi-agent reinforced learning, one of the features, or at least when the things gets really challenging and exciting, is when you have large population of interacting agent, and this agent could be collaborative or competitive, or even the network or this multi-agent could have some network structure. That is something that I'm going to emphasize toward the second half of the talk. And so when you actually think about large number of agents, then this problem of simultaneous learning and decision making in these games is really facing the difficulty of what we call the curse of dimensionality of multi-agent reinforced learning. And this curse of dimensionality is really exponentially growing with respect to the number n. Okay, and so the whole group, the group I look at, the website of this whole group, I was very excited to see half of the main players about multi-agent and the mean field approximation for multi-agent reinforced learning is really in this group, and I'm really excited about it. Okay, and so the idea is, of course, everyone is right. We borrow the ideas from mean field games, and then try to say, well, we can reinforced learning part, we can actually borrow the wisdom from machine learning community, but then what we could contribute from the control community is really using this mean field control of games to approximate this large number of homogeneous agents. Of course, we have to assume the homogeneity and weak interaction just as what we do in the mean field game. But once you have these ideas of approximation of mean field, then suddenly you really get two rich field of reinforced learning and mean field coming together. And we all know that this mean field approximation is good under various criteria, whether it's a competitive game or it's a collaborative game, that we can always show that is under technical conditions, because the underlying propagation of chaos, that you can give good approximation. And therefore, relatively speaking, this mean field approximation will be much easier analytically compared to the original multi-agent reinforced learning. And so the picture here is really showing two different and related games that people are doing. One is mean field game with mean field control, and this is really pretty much the distinction in its mean field limits, and that really trace the development of mean field theory. The earlier work was really based more on Nash, and then later on more development is on the mean field control. And in the learning community, once the ideas of mean field approximation is translated into this reinforced learning or multi-agent reinforced learning, then it's a fertile ground. And then from 2019 to now, already not only there's a lot of papers, and I was actually talking to Matthew. I said, this is such a huge literature. Where do I start to actually review all of them? But of course, there's some very nice recent review papers that I would recommend, starting from the multi-agent reinforced learning, and then more towards the learning from game perspective, and then to the control, and then also with application to finance and economics. So this is really very nice papers. And then if you look at the slides, I'm putting it here. As I said, half of the names are here in the audience, so that's actually saved me a lot of energy. I don't have to review all these papers, but suffices to say that really starting from 2018, I think that was the first paper that really, not really in the strict sense of mean field games interactions, but with only the first order approximation of this paper. And then we had this paper about really using the fixed point method of mean field games, and then also corresponding designing of the algorithm to, there's different frameworks that this group has contributed tremendously in terms of designing and the well-definedness of the games based on the monotonicity assumptions that, and then there's a various policy gradient or mirror descent algorithm that you can borrow. So it's really immediately, there's a huge development in this ground. And then, of course, people have considered entropy regularizations, and then also the mean field studies also follow the mean field theory, going from the stationary mean field games to the ones that without stationary assumptions. So this is a very partial literature, and then you can divide it, depends on how you slice the different works, that you can think about this either from the division of discrete state space to continuous space, or you actually think about it from model-based frameworks, and then all the way to the recent development where you have multi-agent types, and then you can generalize it very much along the way of control or games, where you consider whether you have partial observed informations, or you can borrow this very nice ideas of borrow the mean field approximation with master equations, how you learn it, and then how you actually generalize it to reinforced learning when you have concave utility functions, and then whether you can actually consider flocking behavior. So this is, your group can actually have I think 1 year of a sequence of talks talking about various development here. Okay, and I think then this is really on the mean field games things, and then towards the second half, then of course it's very natural to follow the mean field development, is that one can consider instead of Nash criteria, then whether you should consider also the Pareto, which corresponding to the mean field controls. And of course, there is actually relatively less in that, and this is where I'm going to focus a little bit, starting, from this Matthew and René's papers of discretization, distribution discretization, and add common noise to consider the mean field controls, where this allows you to apply the stochastic dynamics reinforced learning algorithm, and all the way to including our paper that I'm going to talk a little bit about how you use kernel approximation method, how you actually instead consider regret bound, and then how various special cases of linear quadratic can be studied using actor critique algorithm, and all the things that you can borrow from reinforced learning. And I just got recently, when I gave a talk to Santa Barbara, I got to remind of this paper, which I think is very nice about, in fact, not only there's a mean field control with learning, but also there's a connection between mean field games and mean field controls with learning if you actually consider different time scales. And then there's a very nice explanations of how these two are connected with the different time scales. So what I'm going to talk about here is really trying to talk about our latest work when the mean field control. So we first, I'm going to focus, set up the math here. So when you actually think about the mean field formulations behind all this multi-agent one, is really still building on this Markov decision problems, where they only here, when we talk about mean field approximation, is really adding the law of the state. And this is the very important things, that once we have the law that depends on the state of the population, this is, of course, the essence of mean field approximation. And the rest of this is really copy and cast from the multi-agent reinforced learning, that you have the action, and you have the transitions, and you have the reward, and then the reward and the transition functions of the representative agent. Now we are thinking about mean field, so you take a representative agent, then these are all unknown. And then, of course, your admissible policy is going to be this exploration type, that in a sense is going to be mixed type, depends on the distribution of the state. Okay, and when you think about this mean field control with learning, this is maybe I should emphasize on this, is that in a sense why mean field game is relatively easier is because we have this, once you think about, especially from fixed point method, then the reinforced learning is very much easily sit on the first step of control problems. And so, but from the perspective when actually put together with mean field controls, the difference of mean field control and mean field games is really that not only you have this empirical distributions, but in the mean field game, you can think of this. It's very much in terms of computational complexity. It's very much similar to single agent reinforced learning, because what you did is basically fix this, and then with fixed point iteration. But then in the mean field controls, that you really have a deterministic flow from the mu t to mu t plus 1. Okay, the empirical distribution. And that's very important. This deterministic flow also turns out to be very essential, just allows us to borrow many of these theories of mean field controls and then utilize it as a Markov decision problems. And that's precisely what we did in, I think this is 2020, after we developed the mean field DPPs. So first, you have to be happy that analyzing the cooperated multi-agent reinforced learning can be reduced to analyzing mean field controls with learning. So that's of course very similar to the classical mean field control problem. But what I'm talking about here is actually, of course, first, once you sit this multi-agent mean field controls on the deterministic flows, then what you can do is really translating the dynamic programming principle to this setting. And then you try to see what are the Q functions and Bellman equation can be developed so that you can develop the appropriate learning algorithm. And as I said, dynamic programming principle was really the fundamental block for Markov decision problems, and then for reinforced learnings, and then for multi-agent reinforced learning, whether you're using Q value-based methods such as Q-learning, or you use policy-based methods such as the actor critique algorithm. So, and in this, what I want to emphasize is in the domain of mean field controls, this was in parallel in the mean field theories, and Matthew was one of the earlier ones to prove that, to establish the dynamic programming principles for the mean field control. And these, what we actually established, I think this is 2019, again, the same group of people with Guo, and then Xiaoli, and Ren Yuan. So this is the same idea, in fact, as those developed in the mean field control state. The only difficulty or the only tricky part is actually to find the correct corresponding Q functions, and not only to find the correct Q function, but also to say that indeed, if you don't use these Q functions, then the time consistency property will be destroyed. And so the key idea, though, is coming from the classical mean field control without learning. Okay, this we borrowed a lot of wisdom from there. So the key idea is still to lift. Now, when you consider mean field control, you have the state space and you have the action space. And when you actually go into this mean field control things, then because of the distribution that got involved into it, then you just lift the entire state action space into the probability measure space. And this, of course, is the idea that was developed without learning. And the only thing here is, instead of thinking about in the reinforced learning, the first slides that we reviewed is, instead of the Q function depending on the state and action, here you depend on the empirical distributions of the state, and this is probably the ones that make the difference. What is this? This H is the set of local policies. And how can you do this? So the H is if I just think about it, is if you think about H, you can actually think about when you actually have a policy, it depends on the ST and the AT. Okay, and what you can really think about it is actually think about it with if. This is very important because this is if you actually in a competitive game you cannot do this, but in the a collaborative game, what you do is you think of multi-agent reinforced learning mean field control as a central controller problem. Then what it does is you can pretend that you actually can see instead of mu t here. Okay, instead of this, what you actually is seeing is you can observe empirical distribution because you're the central controller, and therefore it allows you to see what's actually. So you given the empirical distribution, then you can actually decide what you can actually see in these. In the action distributions. Okay, I use this. And if you look at this, so it allows you to build this set of the local policies of H that it depends on these actions of the populations. And if you actually rethink of this, then it's very natural that you actually think of the Q functions that depends on the mu and the local policies. Okay, now once you realize this, the rest of the whole Markov decision problems can be reset in this Q mean field control problem. Instead, what you do is okay. You have a dynamics. Okay, the dynamics is going to be, again, I said this H, the local policy, is the important one. That you actually think about the dynamics as an aggregated. Of course, this is your original dynamics, and then it's aggregated over the empirical distribution of this of state, and then aggregated over the local policies. So this is your dynamics. And then you, of course, have this aggregated reward, which is similarly, instead of the dynamics, you have the reward function. And then the reward function also aggregated over these local policies and the empirical distributions. Now you have the dynamics, you have the aggregate reward, and then you can utilize the mean field controls that has been developed in the theory there. That you also have this, you can write this flow properties that is actually deterministic. Now you really come up with a reformulation of the mean field control problems that is really literally being a Markov decision problems with a deterministic dynamics. Of course, now you think about it, it's the same as the lifting idea, except you actually throw every state and throw every possible action on the same table and make it as a flow property. And so you really sacrifice this whole thing because you want to have this Markov decision process formulation. But then you have a huge space that you have to, deterministic space you have to deal with. So, but if you actually, this is the start, but it allows you, if you view this this way, it definitely, you have a Markov decision problem, then the Bellman equation become very natural, except the Bellman equation is not written on the original S and A, it's instead written on the probability distributions, empirical distributions of S and A, okay? So this is the key of the DPP for IQ, and this, of course, as you already see, that the connection of this integrated Q function is very similar. It's very well connected to the classical Q function. If you actually just take the payoff in a very simple case, you take this dynamics and R depends only on the state and action, you can immediately recognize that the relation of the Q function that we have, the integrate Q function, is just the same Q function before as integrated over the mu S and H. Just same integration aggregated as before. Okay, so there's nothing really difficult once you define this H function. Okay, so this is really borrowing the wisdom for existing works. The only question now here becomes, well, you simplified the whole ideas into a deterministic dynamics, but you have a huge state space, a huge space that you have to think about how do you actually design an algorithm, because now you have to really define an algorithm that is on the probability measure space, okay? And even though you think about the state space and action space to be finite, now when you lift this and when you do the integration for the IQ function, so you started having a continuous state action space, okay? So this is really Markov decision problems now with deterministic dynamics, but with this continuous state action space. Okay. So what should we actually do to consider this approximation? Because if you think about IQ function, the reason you have the DPP is that DPP is a recipe for us to write down the recursive equation, and that's usually the way where the policy value iterations method is really designed. So how do you actually approximate this continuous state action space? So the idea is really using the kernel regression method, okay? And the sample complexity, the covering time analysis though here, because of the deterministic dynamics, is much simplified. And that's a trade-off between these two, okay? And so the idea here, of course, this is again borrowing from the classical Markov decision problems, that when you have a continuous state action space, then what you do is you design epsilon net to approximate this continuous one. So you discretize it. And because you have a discretization, of course, your DPP now is actually on this discretized space, and you have approximated kernel regression method based on this DTK is the fixed point method. Now you have this K, this is TK that we call the kernel approximation method that depends on the kernel choices. So you have discretization method, and then you have this, of course, once you have the epsilon net to approximate the continuous space here, then you also, this is a H. Remember, we actually say that now we actually focus on this H functions that is actually a local policy, and it's a set of all the local policies. Then for this action space, correspondingly, you have the induced epsilon net on action space, okay? Now, if you look at this regression, the rest is very easy. You just have to say that I have a Q function that it depends on these DPPs. And then, of course, when I actually do this, I also have to have, what we call the sampling errors and so on and so forth. And so what you need to take care of it is, of course, I have a discretized space, and I wanted to show that when I actually discretize this, and then I have this sum function, this is actually something of this this approximated kernel approximation method. Then I need to show that this whole statement is to say that my original Q function is close to this kernel approximation method with a sampling scheme. And this is actually can be bounded by three ways. Of course, one is the discretized action space, okay? And so I need to actually think about this I decompose it to think about Q, and then I have a discretized one, okay? And what I really need to think about is very important one, that is I need to consider, this is from the original mean field control problem. Then I need to actually think about when I actually discretize this at the probability state space and the induced action space, I can create another mean field control problem. This is what I call QH epsilon. Okay, now this one, I decompose it, then I need to think about QH epsilon. And then I need to consider the kernel regression. So this is the kernel regression that allows me to do this, but then I'm still far away. So I need to also consider, then do the samplings. I need to consider the sampling errors. So if I do this, if I manage to decompose these errors, approximation errors here, then each of this is, you can either consider the errors of the discretization from the discretization and the error from the regression and the projection from the epsilon net. So in this case, you decompose it and you can show that this algorithm can converge linearly to this to a fixed point, which is actually a good approximation, as we showed earlier. That is the error bound is the linearly converged by this epsilon. And what is important is this is independent of the n, of course, because we do the mean field approximation, and then also is sublinear with respect to the space of this. Okay, so that's the convergence and complexity analysis. Okay, and so this
Xin?
is, yeah.
Can I ask a quick question? Sorry.
Yeah, sure.
So in this MFC KQ algorithm, do you use also the kernels, or are they used only at the end to get the gamma K on Q hat epsilon?
I didn't get it. I got the first part of the question. What is the second part?
Oh, sorry. So this Q hat epsilon, is it obtained using the kernel as well, the kernels, or is it independent of the kernels?
Oh, okay. So for each of this one, so we first, so maybe I repeat this. So you have a continuous state action space, right? Mm-hmm. So you do the epsilon net, right? Mm-hmm. Then you have this TK, which is actually the operator for the kernel regression on this epsilon net. Mm-hmm. That's a TK.
Yes. Okay. And you use that after obtaining, you use that on K hat epsilon, right?
Yeah.
So
yeah. And then, of course, the important thing that is here is you consider also the induced epsilon net on the policy, on the action space, okay? And then you can actually consider, this is the corresponding another auxiliary mean field control problem that you can build on this induced H epsilon. Okay, so then you can estimate this sampling one, this is the kernel regression approximation, and then you decompose it into 3. And each of this you can quickly, of course, you need to have continuity. So this is what continuity assumptions on this dynamics, on the reward, and all these usual assumptions that you do for this kernel regression method. Yeah.
Okay.
Does that answer your question?
Yeah. Thank you.
Yeah. Okay. And of course, this one, I know that Matthew, you have the paper with JP and Andrea, where I haven't got time to read since last week when I got it. Where you don't need to completely discretize, completely lift everything into a deterministic one. Instead, you can still develop some DPP in the different space. I think that's a very nice idea. I'm very looking forward to read that paper. So in this case, though, it's really, you really throw everything on the same table. Now, the lifting is really throw everything on the same table. And then you try to find the local structures to do the kernel approximation. But this kernel approximation method, though, give us some ideas to think about really maybe how you actually can utilize these ideas to think about in general when you have a mean field control or multi-agent reinforced learning problem that you have some kind of local structure, and then you can utilize this. So that's itself borrowed Lambda some ideas, but in essence, this idea as a starting point is really lifting everything and throw everything into a deterministic Markov decision problem, and then using kernel approximation method so that you can get kernel-based Q learning with linear rate of convergence. Okay, but in terms of the next 10 minutes, I want to talk about, if I have time, is actually to talk about how these ideas of local age policies and the aggregations of this reward dynamics could allow you to actually tackle certain multi-agent reinforced learning problem when you have actual network structures. Okay, and this is what, of course, this is the key things that really allow us to think that way, meaning that instead of thinking the Q functions, we have this IQ function, which is really integrated over the local functions over the empirical distribution and local policy. So how do we actually use it? And this, I'm very happy to have 10 minutes to share with this. So in general, if you think about this is, well, you have a theoretical guarantee with all these ideas, but still you think about it, it's still somehow you would think that it requires too much information, and some of them may not be really useful when you actually, for the agent, when you do the trainings. Can you actually utilize this idea, but then still control the sort of local information and the global information in a more efficient way based on some more structures that have network structures? So this is what we actually consider. This is the latest work, which is you think about this Ubers or Lyft, where you have a lot of agents. You think about agents as being drivers, okay, and their locations are their states, okay. And then, of course, drivers need to go from one place to the other. That's their job, okay. Now, if you think about this, and if you think about the dispatch of, or even in Amazon, where I work for, you have all the carriers, and you think about the control of the platform, how to from the platform perspective, you want to optimize this, all these dispatch things. So you still have the corporate games, and you still have the characteristic of large population, and you can still utilize the thing locally. The drivers and others are sort of homogeneous, at least locally. Okay. Now the network structure comes in the sense that there is this interaction of this of drivers with the local traffic or demand information that one have to take care of, and also the network structure is that drivers has to move from one closest neighbors to the other, usually by a certain connecting nodes. So there's a network structure that when you think about the mean field approximation, in general, you don't think of this, but there is a network structure, okay? So how do you actually learning using similar idea that we had before, but then you try to develop it so that you have the network structure. So this is what you can do. And this network structure that I want to emphasize is different from social network structure, okay? So in the social network structure, we call it a network of agents, because people are connected on the social network. This connection is by the agent. And the one that we talk about is the network of state, in the sense that from the agent perspective, I'm actually moving. So where I'm now in Berkeley, and then I could move next round into San Francisco. So my state is actually stochastic and evolving. Okay, so if I actually focus on this network, then I will actually focus on the state rather than agent. Okay, how do I take care of this moving state of the agents? So let's consider the agent an agent in the system, and then let's still consider a state space and action space to be finite. What I consider is I can consider an undirected graph. Where is the state of agent? And then the edges are the ones that connecting the agents when they are connected. Okay, and when I think about distance of this is of course the two nodes, the distance between me and the next agent is actually by how many number of edges that are connected, and I take the number of edges in the shortest one. Okay, that's one. And if I have the distance, now I have actually metric space, and then I could actually define, of course, once I have the edges, then I can define what is the nearest neighbor of a particular agent at any time. Okay, so given time, I'm in a particular state, then I can define my nearest neighbor. And if I can define my nearest neighbor, then I can define my nearest k neighbors. Okay, the nodes for which this is less or equal to k. Okay, so now I have this network structure depends on the nodes and depends on the distance. Then what I can do is now, this is what happens. I need to depend, I can define the reward function instead of depends only on my state and my action, but also depends on my nearest neighbor nodes. Okay, this is the empirical distribution of my n, the nearest neighbor. Okay, and also if I do this, I know that I can write down with the empirical distribution of my nearest neighbor, then I can actually write down the dynamics of my state because I always move to my nearest neighbor. Okay, so I can write down the dynamics. And now, if you look at this, the difference between my usual mean field control framework is instead of the state and action, I have also the distributions, but this empirical distribution is actually dependent on the local network structure. Okay, and the only thing I need to do is I have to retranslate the mean field control problem, which I initially successfully translated into deterministic Markov decision problem. Can I actually rewrite it into this network structure? And the answer is yes. Okay. How do I do this before I come back to this? Is I look at the system. Now I have all the agents, say 1 to 7. And instead of focusing on their state, on their agent, I actually group them by where their state is. I suppose I have finite number of state. I group the agent as a team. If the state 1 has 1 agent, so be it. And if actually I say agent 2 and 3 are in state 2, then that's another team. And if several agents are sharing in the same state, that's another team. So instead of looking at each individual agent, I group the agent into a team, and then this multi-agent reinforced learning mean field control problem becomes a game of teams. Okay. Now, instead of n players, I think of this game as S-team. Okay. Now the question is, how do I actually do this? So I reformulate, so I can, the important thing, as I said, this is very important initially when we actually see the connection of this. If I have this individual integrated Q functions that are dependent on the local structures and dependent on here empirical distributions, then this integrated equation allows me to rewrite the Markov decision problem, which is the expected value of the payoff function, conditions on the team or condition on the state, and then do double integration, double conditioning, so your objective function doesn't change. Okay, and in order to do if we do that, then when I actually do the Q tables, then instead of looking at the entire game, I actually have a much smaller one, the Q table for the team. Okay, while smaller one, if I can assume this one, the exponential decay. So I need to ensure that if I'm in a state S and my Q table focus on the state, then I need to have to ensure that I'm able to focus locally, because I have to use this assumption is very much popular in general graph theory when people study it, which is called exponential decay properties. And usually it's assumed that the network structure is loose, that the distance of A to B will actually, or the payoff will be exponentially decay with respect to the distance of the two nodes. And in this particular case, when you actually look at the infinite dimensional discounted problem, what is very nice here is it naturally have this Q functions exponential decay properties. So you don't even need to assume or impose it. So you utilize this, and you utilize this teamwork, and you utilize the Markov structures with double conditioning. Now, you know what you can do. Now you have the network structures. You can just borrow this actor critique based algorithm with, well, this is important, with neural network approximations. Okay, and you use, you know, this I don't need to teach anyone from reinforced learning, that you have the actor critique. One is the policy, the other one is the function value Q function iteration method. The only thing that we parameterize here with the two layers of neural network is because there are theoretical studies that shows a convergence of the shallow one layer of one hidden layer of neural network. But these studies, I want to emphasize, is there are recent studies by a group in UCLA that actually shows for deeper and wider a deeper neural networks that they have some tricks to show convergence and analysis. If you use those, you can borrow, so you can also adapt the proof we have here to establish the convergence analysis. But here, the convergence analysis is really we look at this the number of iterations to be the polynomial with respect to the width of the one hidden layer, so the two-layer neural networks, and then you can prove the convergence for this, both the actor and the critique, which I didn't critique is here. That you can see that is based the convergence rate depends on the weights of the layers and depends on the discount factors, okay, and this also depends on this sublinear with respect to the states and the action. And then this is actually, I forgot to introduce, this is the batch size of your oh, here, I wrote it. It's a batch size, okay? And of course, you can see that K, the convergence depends on the gamma of K plus 1. K is the nearest truncation, neighborhood truncation of Q functions. So you can see that it depends on if the network is loose, is not very tense, then the convergence is faster. But if it's actually very tense, a very connected graph, then the convergence will be slower. Okay. So anyway, so this is. And also, I want to emphasize that you don't necessarily need to be just two layers, one hidden layers of neural network. You can adapt it to the latest development of the neural networks and still develop this actor critique algorithm and derive similar convergence results. So this is what we actually developed for recent work that you can actually, if anyone is interested, that we have, it's still under review, that we can share that for this network structures for multi-agent reinforced learning. And this was really already there. This one is going to appear in OR, and this is going to be appear in SIM data science about the DPP and the algorithm. And of course, there are a lot of works that I cited from this group on the various learning of mean field games and mean field controls. And I'm very looking forward to the discussion and learning more from the group. And thank you very much.
Thank you very much for the very nice talk, Xin. I don't know if there are questions. So just a reminder that the talk is recorded, but of course it's great if people want to ask questions, and they will be recorded as well if it's fine for everyone.
I come to see, where do I get back to this? Oh, okay.
We can still hear you. And yes, Thanos, you have a question maybe?
Yes, I have a question. Thank you very much both for the seminar and the very interesting presentation today. In fact, I have two questions. The first, it's both about the mean field control of the multi-agent system, the MARL. The first is about the error when you get in the approximation. You show us that you could separate the error in the different approximations. And the error regarding the approximation of the space, the state of the space. I mean, if you could say a little bit more about the errors that you get. And this question is related to when you want to put this into the machine, like when you want to run experiments by the algorithm. Are you still going to get this linear error in the end? And the second question, or maybe I can ask the second after like the first. It's up to you. I can ask both now. And the second is about the exploration exploitation.
Okay. So in the first one, okay, what we actually have, this is a TK hat and Q epsilon, right? So the TK hat itself is about
for me, I cannot see the screen if you are writing.
Okay. Okay, so now let me try to see. Oh, okay, I can recover the share screens here. Okay. Where is it? Okay.
Yes.
Okay, you can see, right?
Yes.
So, I guess what you're asking here, so this is actually about the simulation, right?
Yes.
So this Q epsilon is the approximation, but then actually this Q epsilon is a sample error, right? You have a simulation error. And so when you actually think about this, what we actually show is this, the errors is upper bounded by C epsilon, where this is any epsilon dependent on this is epsilon prime is coming from the greedy policy, and then this is delta is the probability of this of the errors that you're trying to say. I don't credit when you say that in practice the actual error that you are mentioning. What is that?
It is connected with the second one. Like in the computer, when you put this in the computer, you don't have, at least actually you don't have the covering time assumption. Like because in theory you make the covering time assumption that you visit all the balls that you separate, but in the machine, like I suppose that it takes time to visit, so you have this question of exploration exploitation.
Okay. So in this one, when you actually have the covering time here, the covering time is because of a deterministic, you only visit once, no? You don't need to say that the covering time is to visit every state at least once. Here, because of deterministic, you just visit once, and that's enough, right? So this is actually simplify your covering time analysis.
So what you are saying, just to clarify, maybe to make sure I understand correctly, is that here, because at the level of the distribution, the MDP is deterministic. You just need to visit once every point in the epsilon net, and then okay, and then you know for sure the reward at the mean field level and the transition at the mean field level. Is it?
Exactly.
Okay,
So so the key here is but then of course you reduce the complexity in terms of covering time, because this is deterministic. You just have to visit everything just once, not at least once, because it's deterministic. But then of course you pay the price of a huge space, which is actually discretized from this continuous action state. So you need to do the kernel. And therefore, this epsilon net, this is basically the error of epsilon is really coming from this epsilon net, this kernel approximation. So we also find out maybe something related to it. I'm not sure I answered. Is when we actually do this kernel regression, we found out that depends on the problems and depends on the network structures, that your different choices of this kernel approximation kernels could be very differently. Okay, and the approximation errors and it very much depends on your choices and on the problems when you actually choose this particular kernel approximation functions. And that's one of the reasons that we realize that the age policy is important, and also it gives us the hint when we actually look at the network problems that really the local neighborhood information is very important to do this, to this graphs or mean field approximation with network structures. So it does depend on this epsilon, the choice of this and the choice of the kernel regression, which is in some way related to the closeness or the tightness of the network. Does that answer your question? And the second question, I don't quite, I didn't remember. What is the second question?
No, you already answered, right? Because it was about the exploration exploitation, but it was connected.
Okay.
Thank you very much.
Yeah.
Okay, nice. More questions or comments? We are a little bit over time, but if I don't know if you still have time, but is it okay to ask more questions? Xin?
Yeah.
Okay, great. Thank you. Sarah, do you want to?
Yes, hi. Thank you for your talk. It was very interesting. In particular, I didn't work that much on mean field control, so I'm happy to learn more. I was wondering what happens if S, the number of teams, is large.
What you're wondering? What?
If
Sorry,
what happens if the number of teams becomes very large?
Oh, okay. Yes, okay. So that's a very good question. So you can see that the number of teams. So you actually see that it's a team game. So you do this, but really this is dependent on the state of these teams, right? Because the teams is really becoming dependent on the state, and the only thing we could show here is actually this is sublinear with respect to the team. S. Okay. Yeah. So you are thinking about state, and hopefully the trade-off here is really thinking about if you actually have like in Amazon, when we actually have a destination of carriers, right? So usually, in fact, from A to B, that's actually less than the numbers going from A to B. So you're thinking that focusing on the team here is actually better than focusing on focusing on the state is better than focusing on how many Uber drivers are going from Oakland to Berkeley. It's only Berkeley, Oakland. So the state actually is relatively better to think about than thinking about the hundreds of Uber drivers between Berkeley and yeah. But you're right. So this is still sublinear with respect to the state.
Okay, thank you.
Yeah, and of course, the one wonders is what if I actually have a continuous state space, right? We still have this constraints that is less than infinity. But what happens when you actually consider continuous space or polished space or whatever? And I think things has to be reapproximated in some other ways. Yeah.
Okay, thank you very much.
Yeah, thank you. Yeah.
Yes, Mathieu.
Yes, thank you for the nice talk. I have a question. At some point, your value function depends not on the state, but on the distribution of the state. So basically, your new state belongs to the simplex. And this makes me think about partially observable Markov decision process, where you have similar thing in the sense that you have a stream of observation, and then you will use a belief state, which belongs to the simplex. And in the case of POMDPs, you have a special structure of the value function. Specifically, it's piecewise linear. So the setting is really different. But I was wondering if you have something similar in this case, some kind of special structure.
Yeah, it's a very nice question. So as I mentioned that when we actually can try to read the important thing that when you actually can borrow this mean field control. So mean field control that we manage to make it as Markov decision problems, right? And then when we actually reformulate this as a team game, so we actually still expected value of this is really dependent on the network structure, right? SIT, so STI, and so the way that you can redo it is, of course, you know that I would not change the entire Markov decision problem because of I can reconditioning, and that's key. And that's where all my integrated value function, integrated reward function, everything could be by a very complicated computation, but still a computation you can reformulate. Great. So now, when you actually come to just like in the earlier work that your group has been doing in terms of with partial observations, okay, then this becomes not completely straightforward. Okay, so you need to redo this part because now you have partial information, and then you actually, instead of a double conditioning, because now you don't really know everything, how do you actually estimate this part? That will become very interesting to do, but we haven't considered that partial observation stuff because now you actually have a filtering things to come in, and then you need to probably, I don't know whether the latest generalization method that I mentioned, I think I mentioned it here. Here, I think, where did I do? Data generalization, this here, right? I don't know whether this one can be, for example, if that's what you had in mind, or whether some element of that could be incorporated with our approach, and then combine these two, can study the cases with partial observation. But it's a very nice question. Yeah, I think that's something that we didn't do.
Thank you.
Yeah, thank you.
And related to that, just to clarify, in your model, I think it's on slide 34 or something like that.
Oh, okay. So sorry, I'm very slow. I can only do this way.
About the network structure, right?
Yeah.
Exactly here. So here it is really in equations 1 and 2. It is really an assumption in the model that the reward and the transition depend on the local. Depend on the distribution locally, like in the neighborhood, right? It's not an approximation that you make. It's not that it depends on the whole distribution, but you replace and you approximate.
Yeah.
It's really part of the model, right?
Yeah, yeah.
Okay.
This is
okay,
very important. So this is we have to do the nearest neighbor, because otherwise this dynamics, this one will be much more complicated, right?
Right.
This network, you really have to think about, if I go from Oakland to San Francisco, I have to really pass the bridge, right? So this is where that we actually have to rely on this nearest neighbor ideas. And because of this, then of course, correspondingly, you would think that it's related to on the empirical distributions of all your neighbors. So this is the thing. Yeah.
Yeah, makes sense. Thank you.
Yeah. Thank you.
All right. More questions? If you want, you can ask questions in the chat too, if you don't want to ask directly. But
Yeah, I'm really happy that to really be able to talk to the group, because I think this group is it's one of the group in the to do the mean field and reinforced learning. I'm really looking forward to any feedback or anything. Just send me emails if you have any questions or anything. We're very excited to hear any feedbacks on this.
well, we're very happy to have your talk. So thank you very much
Thank you.
again.
Maybe a quick question.
Yeah.
You mentioned that you can decompose the Q function, the IQ function,
Yeah.
as integrating all the Q function of the local policies. So
Yeah.
do you need to learn these local policies?
So I have this Q functions. Yeah, so I have these Q functions. Yeah, so this is basically the way that when you actually have Bellman equations, right? So what's your question about this Q function?
So I think the equation on the next slide, maybe, or maybe this one, like.
Yeah, so this Q function is actually dependent on this the mu and the h. H is the local policy, right? So this is empirical distribution, and so in the way, so when you actually the way that is this is from this Q function, you can already see this is a Markov decision problem, and this is the reward function. The reward is also aggregated, the original reward functions, and aggregated over the empirical distribution and the local policies. And the same as the dynamics. Now it's a new dynamics and over this. And this is where, of course, then the only thing is when you think about the mu t, then it's actually deterministic. So it's a Markov decision problem with the aggregated reward, aggregated dynamics, and with a deterministic flow.
And how do you get the local policy?
How do I what?
How do you get the local policy? Like, how do you...
Oh, the local policy is defined here. So if you actually think about this h, so you think about the original function, it depends on the mu t, right? So you actually think about, this is actually critical. So when you think about, this doesn't work in the mean field game, but in mean field control, what you think about is from a central controller perspective, once he observed the flow of these of the empirical distribution, then you can actually fix this. So initially, your policy is pi t of mu t and let's say mu t and the at. Okay. Now you actually fix on this. Then you can actually just observe the mu t. Then you can view it as the pi t depends on the action, and that's why we actually can set this. Yeah. So, but this only works if you actually are thinking of mean field control, because this is a central controller, and the central controller is observing the empirical distribution of the entire state, and then you actually give the policy to each individual. So that's possible in this setting, right?
Okay.
Otherwise, in the mean field games, that each individuals cannot really observe the entire state, right? So that's the key thing here.
Okay, thank you.
Yeah.
Okay, well, thank you very much. I guess maybe we could stop here. Yeah, well, thank you again. Xin, let me stop the recording.
Thank you very much. It was a big pleasure for me to meet everyone here.